Hey guys, as promised, I'm going to take a close look at FRQ questions 1 through 5 from the 2017 assessment. So let's get started because this is going to be a long video. Number 1A is asking us to describe in context what the words positive, linear, and strong mean. uh, what those three words mean in relationship to the scatter plot, I don't know, correlation. So let's talk about the word positive first. So I have in front of you an example of a student response. Notice that they're using context and they're talking about as the x-axis increases, what is happening along the y-axis. And they're using squishy words like the data suggests, it's approximately, it's going in an upward trend from left to right. And you want to use the context in terms of x being what the length of the animal and the y-axis is the weight of the animal. And so as the x-axis increases, as the length increases, the weight increases. Let's talk about the word linear. When we come up with a prediction equation, we want all of our data to hug closely around the line, and we want it to appear as if a linear pattern is taking place. So you want to use words like line, the data is close to the line, it doesn't deviate too much from that actual pattern. And strength is talking about correlation. So as one goes up, the other goes up, or as one goes down, the other goes down. So our residuals are going to be small. So you want to address that as well. Looking at the same student's response to Part B, this student got full credit as well on their response. Interpreting slope, you want to address that for each additional 1 unit, the x-axis increases. You always reference the x-axis first in your interpretation, and as it increases by 1 unit, what is happening along the y-axis? Well, in this case, our slope is positive, and it's going up by 35 units. So what is your y-axis? Your y-axis is the weight of the wolf, and these are all approximations. So again, another good squishy word is approximate, or about, or on average, it's going up by 35 kilograms for each additional 1 meter in length that the length of the animal is increasing. And the last part of problem 1, the same student earned full credit. I probably wouldn't have approached it necessarily in this exact order, but I would have reached the same conclusion. So let's talk about this. You know that the length of this wolf is 1.4 meters. So plug it into your prediction. Like, what is it that I'm going to predict that this animal is going to weigh? So you see that in the third line of the student's work. So the equation, the prediction equation says take negative 16.46, add 35.02, but multiply it by how long the animal is. So in this case, I predict that this wolf is going to weigh 32.57 kilograms. Okay, great. That's what I predict. But then the problem goes on to say, wait, your prediction was off by negative 0.9 or negative 9.67 kilograms. So what was the actual weight of the animal? So in this case, remember that neat little trick, observed minus expected? Well, going up here, this is my observation, okay? This is my expectation. and that's going to give me how far off I am. So I actually don't know what I observed, right? But I do know that I expect the animal to weigh 32.57 kilograms. So you would say y minus 32.57 kilograms equals negative 9.67. And then just use algebra to find your y value. Always, always, always remember, what did I observe minus what did I expect? That, you really want your error to be nothing, right? What did I observe minus what do I expect? I want it to be 0, but in this case it wasn't 0, it was negative 9.67. So your equation again, I don't know what I observed because it's asking me what it is, but I do expect the animal to be 32.57 kilograms, and that is equal to an error of negative 9.67. I would have rearranged the thought process. In the end, your answer is 22.90, and you have to show work there. So make sure you feel comfortable about that. Guys, I hope that helps on number 1. Okay, let's look at number 2. Question number 2 is asking us to construct a confidence interval. It tells us 95% confidence. You got to run panic, but what I find interesting in this student's response, this student got full credit, and from year to year the rubric changes. So they defined the parameter. The parameter is let P equal the true population proportion of all customers who fill the cup with soda rather than water. We've actually done this one in class, so hopefully you remember how to do it. They went in a different order, but I teach you guys to check your conditions next. Selected a random sample. Remember, please just copy verbatim in quotations what it says because you don't want to lose points there. You have to check for normality. I always check for normality before independence. Normality is, since this is proportions, we're going to do n times p and n times 1 minus p. Those both checked out to be greater than 10. And then for independence, you just want to do 10 times your sample, which is 800 people, needs to be less than the population at large. So check this out, pretty simple. Then the student named the test. It's a 1 proportion z interval. Notice they didn't even show work. They didn't even give us the student didn't write down the formula, nor did the student plug any numbers in. They just put down the interval. In this particular year, they weren't looking for that. So they were just looking for the actual interval. And then in the end, I'm 95% confident that the interval from blank to blank is going to capture the true population proportion of all customers who fill the cup with soda rather than water when asking for water. So that student got full credit on that. Oh, so part B. Remember this? We struggled so much with this question. What it's asking is, hey, if 3,000 people come in and ask for a water cup when placing their order, how much is that going to cost the company if they end up filling it with a soft drink instead? So it says that the cost to the company is 25 cents per cup. So let's go back to part A and think about the interval. This interval here is the true proportion. We're predicting that this captures the proportion of customers who are going to tell a lie. So about 18% to 38%, or 19% to 39%. So if you know the percentage of customers, and then in part B it says, hey, 3,000 people come through, well, how many customers is it if we're predicting 19% to 39%? So find 19% of 3,000, find 39% of 3,000, and the student did just that. So they're predicting between 565 customers to 1,160 customers out of the 3,000 are going to tell a lie. That's the number of customers. And if each of those customers tells the lie and it costs 25 cents per customer, you now got to multiply 25 cents on each of those. So this is cost. So over here, that's people. Here is cost. So it's going to put a burden on the company of anywhere between $141 and $290. And this particular student showed the work and then wrote a little statement afterwards and received full credit. Okay, I love number 3A. Hopefully you guys will get a normal distribution question as an FRQ. I wouldn't approach 3A like this student did, but this student got full credit. I've taught you guys to draw a normal curve. Draw it just like this student did. It's asking for a probability greater than 137. So this looks great right here. Probability that's bigger than 137. Shade it. Make sure you shade it. Put your mean in the middle. The mean is 133. Put your standard deviation on your curve. Get full credit. Shade it to the right because it's a greater than symbol. And then label. If you label it, then you don't have to do z-scores. So when I say label it, I mean tell me what your lower bound is. You got to label it LB. Lower bound is 137. Upper bound is infinity. Your mean is 133 and your standard deviation is 5. Plug it into your calculator as a normal CDF function. The end, you should still get something close to that probability, somewhere maybe around 21%. If it's not exact, that's fine. Just make sure it's close to it and you show your work. So part B takes the probability question and flips it on its head. So now it's talking about this new distributor, and it's going to provide melons from non-organic farms. Okay, so the probability that it comes from this distributor K and having a diameter bigger than 137. Now remember, the problem above was dealing with a diameter of greater than 137 from distributor J. So we claimed that the probability that it's greater than 137 from J is 21%. Down here, the same question, but from a new distributor, it's 84%. 70% of the melons come from J and 30% of the melons come from K. So most of them come from J, some of them come from K. The meat of the problem is you want 30% of the melons and have this probability of 0.8413, or we got 70% of the melons and 21% of them are going to have this particular diameter. You just multiply each of them, add them together, and your final probability is 40%. If you want to do a tree diagram in this case, you could. You could say they either come from J or K, and then do your tree diagram, multiply everything out, and then add up your answers. Okay? If you need help drawing that tree diagram, actually, let's just go ahead and do that. Let's see what that looks like as a tree diagram. So we have melons coming from J, and we have melons coming from K, right? And I think we said 70% are J. I'm going to double check that, and 30% are K. So let's go back and see. 30% are K. Okay, so I did that part right. And then it says the probability that it's the bigger diameter from K is 0.8413. So that's where large diameter, right? And if you wanted to find this number here, you would just do 1 minus 0.843. Not going to waste your time on that because we don't even need that. So again, large. And I think on the J one, didn't we calculate 0.2119? Now you might have gotten a different number. The point is, on your normal CDF when you run it, if it's a little off, you want to put that number where I just put 0.2119. What you're going to do is you're going to multiply these two here to get a number here. And then you're going to multiply these two here to get a number here. And since it's an OR statement, you end up adding them together. So if visualizing it and seeing it as a tree diagram helps you, by all means do that. So let's go back up to the problem. Answer is roughly around 40%. Part C is one of those given statements, and this student did an excellent job. This is exactly how I would teach it. It says given, so you know that melons selected at random from the grocery store is greater than 137. That's given. So that's why after the bar, whatever's given to you goes on this side. It says, what's the probability that it comes from J? That goes on the front side. So on the top, we want to know J and 137. And remember, that number was going to be 0.7 times 0.2119 because it has to come from J and it has to have a bigger diameter. So that's why this student multiplied. On the bottom, it just has to have a bigger diameter, and we got that answer in part B. These problems with parts A's, B's, and C's, they feed off of one another, so just keep that in mind. Guys, that was a tough problem, but hopefully I cleared up any confusion. For question number 4 in 2017, holy cow, there's a lot to read on this problem, and it takes probably a couple passes rereading it before you can really wrap your head around it. For part A, when it asks you to describe distributions, you kind of indirectly want to use SOX, but not explicitly say you're using SOX. This student here did an excellent job of comparing the chemicals across the 3 sites using SOX, but using it discretely. So you want to use comparative language, like talk about the centers on all of them, talk about the spread on all of them, who has it bigger, whose is bigger, whose is smaller, you know. So read over this response. Yours does not by any means have to match it perfectly, but you do want to talk about like spread. When it comes to box plots, don't so much focus on the range, focus on the IQR. You want to talk about centers of spread. The centers, sometimes medians on box plots is smarter because you don't know where the mean is. So talk about the medians, talk about the IQRs. This student even talked about range also in addition to the IQR, which is pretty cool. One thing you don't want to talk about is shape because you don't know the shape of a distribution by looking at the box plot, okay? That one's tough. Oh, this problem's a little sneaky. Okay. So you got to read it a lot. Suppose an analysis of the clay reveals that the sum, that's key, the sum of the percents of the three chemicals, so you're adding X, Y, and Z, is 20.5%. Based on that knowledge and the box plots, do you think it's site 1, 2, or 3? So you're dealing with box plots, and you got to figure out which one comes closest to 20.5% for X, Y, and Z. This student did a jam-up job because the student looked at the median measure. That's great. What's the average? What's the center number? And so this student chose site 3 because when they added up the 3 medians for X, Y, and Z at site 3, it came pretty close to 20%. The others did not, and the student talked about those. So you want to make sure you talk about why you're choosing 3 and why you're not choosing 1 and 2. Ugh. And they used medians of measure because that is the best predictor when looking at a range of data. Super interesting.